I want to present to you context for the adoption of digital twins in power systems, of course, and their related challenges. So we could say that simulation technologies have evolved as computing technologies did. And there has always been a need for simulation tools to evolve with power system technologies. But on a simplified timeline, as the one I'm showing here, we see the evolution and purpose of, let's say, EMT simulation, HIL testing, and Phasor simulation. EMT offline simulation has been used for fast transient analysis, and nowadays we see it being used more and more for system studies with complex control systems. There is digital real-time EMT simulation that has emerged in the past for HIL testing of complex control and protections, testing of FACS and HVDC control replicas. Still today, we see phasor time simulation is widely used for dynamic security assessment and planning studies. But there are experts that are starting to see limitations and are looking towards EMT simulation to overcome some of the issue. And part of these issues are due to the fact that phasor simulation will assume that the grid has large inertia with a majority of conventional rotating generators. So, and it also assumes that the system is perfectly balanced if it is a positive sequence simulation tool. These assumptions may no longer apply with higher penetration of inverter-based resources or IDRs to assess power system stability. So there definitely are opportunities to adopt new ways of analyzing grid security now, and digital twins may be a solution. In modern power systems, we see more interactions between faster or local control and protection systems and coordination with wide area control and protections through complex communication systems. We also see more IBRs within centralized power plants at the transmission level, but also distributed throughout the distribution system. And all of these sources will decrease total inertia as a result, and reaction times of the connected sources will also reduce. So as they require faster control and protection functions that will interact with the rest of the system, it can seriously affect stability. So, So here is a definition of a digital twin that could help analyze the complex modern power system. A digital twin is a virtual representation of the system to better understand and predict its behavior. So what could be some ideal attributes of or features of a power system digital twin? Here we suggest three main categories, which are real-time adaptability, observability, and predictability. Real-time adaptability implies that the digital twin is synchronized and connected to the grid. It should be able to adapt based on current operating conditions in real time or near real time. It should or could adjust its internal models based on parameter estimation methods. The observability attribute is to say that having a digital replica of the real system can allow better assessment of all system states that monitoring cannot offer. The observed variables on the digital twins can be analyzed with greater details, with higher sampling rates, with less of the traffic and latency limitations of the monitoring and communication infrastructure. Predictability, because a digital twin should continuously assess the most critical potential fault scenarios and help prevent system collapse. As an example, it could assess multiple scenarios based on actual operating conditions, let's say at every 5 to 10 minutes. And here's an example for a power system digital twin with these attributes. We can see it has real-time adaptability as it is synchronized and connected to the power system. It adapts to the changing conditions and includes parameter tuning. Here, the observability and predictability would be ensured mainly thanks to real-time or faster than real-time simulations on the cloud or high-performance computer. The digital twin provides additional data to the operator through multiple scenario assessment, which will help in decision-making. This may seem difficult to realize, especially for a digital twin that would use detailed EMT models, but the reality is that processing and simulation technologies are now available to deploy this concept. But model fidelity is still a very important challenge. Some utilities have limited amount of data from the OEMs. The current practice is to use generic models in Phasor domain, and reliability councils such as NERC are enforcing rules that require model validation through on-site testing. These rules may have significantly improved dynamic assessment with conventional generator models, but the proposed generic models in Phasor mode may not necessarily represent power electronics control and protections properly when it comes to IDRs. In certain cases, manufacturers are requested by utilities to provide black box models using the real code of their controllers, but these models are currently not interoperable from a simulation tool to another. So there may be a need to propose new rules regarding OEM models and even adopt new standards for accepted and interoperable models that could be used for grid security assessment. Moreover, these models may come in various versions with different sets of parameters. There is actually no guarantee that the settings of the model are exactly the same as those of the power plant at all times. There can also be different departments of the same utility working on system studies, and they need to use the same models in their adequate contexts. So the use of a centralized model databases within utilities should be considered. Another important challenge I mentioned earlier is the questionability of current simulation techniques used for security assessment. Phasor simulation alone has major limitations when it comes to simulating systems with high penetration of IBRs, and EMT is gaining much attention. So it is important to consider a change towards EMT simulation or a combination of Phasor and EMT simulations. Using real-time simulation technology, which allows both simulation domains, seems like a promising solution. There are also challenges related to the test coverage and contingency analysis, which I listed here, but I will discuss that using the following illustration. When it comes to the simulation of hundreds or thousands of scenarios, especially when adding EMT simulation in the mix, HPCs and cloud computing may help in deploying parallel simulation runs, for instance. But if there is no intelligent selection of the scenarios, we are still looking at a compromise between test execution speed and available computing resources. So there clearly is a major opportunity here to start looking at artificial intelligence to optimize the simulation runs and identify the most critical cases. And that's it for me. I'll be quite happy to hear your comments, opinions, and questions at the end of the webinar.